Welcome to Deforestation and Feedback Loops, which is our 64th Crossing Thin Ice podcast. Rainforests are a major part of the planet's ecosystem, and today we're looking at how the role of rainforest goes far beyond biodiversity, influencing both global water and carbon cycles. I'm joined today, as always, by Max Rudolph, who will drill down on the complex dynamics and feedback loops that we find when we look at rainforests. Human-driven deforestation has accelerated sharply in recent decades, disrupting ecological balances that were stable for millennia. Climate-related feedback loops can magnify environmental changes, sometimes in ways that are hard to predict. The Amazon rainforest, which is our focus today, is approaching a critical threshold where its ecosystem could shift irreversibly. Such environmental tipping points carry wide-ranging implications for agriculture, economics, and long-term risk planning. But before we get started, we do want to remind you that nothing in today's podcast is investment advice. We are here to educate and entertain risk managers and senior officers at insurance companies with our opinions about risk and risk management topics. So let's get started.
Rainforests can be found on every continent except Antarctica. They come in two types. Temperate rainforests are located away from the equator, so are cooler and receive less, though still a lot of rain. The soil holds a lot of nutrients since decomposition is slow. Examples on the U.S. West Coast include Olympic and Redwood National Parks. Tropical rainforests are hot, humid ecosystems that can receive 400 inches of rain each year. Much of the biodiversity lives in the canopy. Organic matter decomposes quickly, resulting in a thin layer of soil with few nutrients. If trees are removed, the soil becomes even more barren and susceptible to flooding. It is unsustainable beyond a few years for agriculture and ranching use because it quickly is depleted of nutrients. The Amazon jungle is the largest tropical rainforest. Rainforests are important as habitat, but what's interesting to me is their role in the water cycle. Water in the Amazon comes inland from the Atlantic Ocean and falls as rain. Roots absorb the water, which then evaporates from leaves to form clouds. A rainforest recycles its own moisture, absorbing it during the hot daylight hours and releasing it into the atmosphere at night. Rainforests store vast amounts of carbon, but half have been destroyed in the past 100 years due to fire and activities including logging, cattle ranching, agriculture, and mining. This destruction continues today as more forest is cleared. Prior to the industrial age, there was a balance in the carbon cycle that maintained global temperatures as the sun's radiation provides energy for warming and photosynthesis for natural carbon capture and oxygen release. This balance was stable for the last 10,000 years until we began releasing long-stored carbon by burning fossil fuels. These greenhouse gases keep the sun's energy in the atmosphere and oceans, with warming driving drought conditions and wildfires. The rainforest ecosystem is built around water. If it loses the core area needed to maintain the moisture, it will revert to savanna, changing wind and weather patterns worldwide and interacting with climate change in unexpected ways, some good and some bad. That is the concern from shrinking the size of the Amazon, that it will upset the carbon and water cycles. I've previously written about the climate impact from feedback loops involving the albedo effect, where melted ice causes more sunlight to be absorbed, and permafrost melting, where frozen methane is released as the tundra warms. Other concerns have included slowing ocean currents and drought-fed wildfires. Another complex ecosystem with global warming implications are tropical rainforests. Each of these trends is subject to a tipping point that is hard to anticipate in advance. Tropical rainforests are fragile. The Sahara region in Africa transitions between dry and wet due mainly to changes in the Earth's tilt about every 20,000 years. But agriculture, mainly grazing, may have accelerated the most recent drying process. The Sahara was last a lush green, fed by monsoon rains, about 11,000 years ago. The Amazon in particular is at risk of becoming a savanna within a generation due to deforestation. Forests are being cut or burned, warming the atmosphere and reducing freshwater availability as a direct consequence of this feedback loop. Other places, like North America, will see indirect impacts as weather patterns change to reinstate a stable balance. Scientists extrapolate the tipping point from deforestation in Amazonia to happen within 15 years. Emerging risk scenarios being built today should consider a collapsing Amazon ecosystem as a stress test. How will changes in weather patterns impact agriculture and economic outcomes? This is not a storyline that we're comfortable addressing today. We haven't been trained to do that. We'll need to expand our knowledge about changes to climate and its ramifications to food supplies, mortality, and morbidity, economic growth, and finally, interest rates. Narrative scenarios will become more important in years to come. Interactions between risks are becoming more important, including feedback loops and changing trends about assumptions. Even if the analysis is qualitative, it is important to expand our thought process to include environmental risks along with other factors driving regime change.
All right, Max. Well, can you tell us more about how human activities, particularly from agriculture, can accelerate the natural climate shifts in ecosystems in places like the Sahara or tropical rainforests?
Sure, when ecosystem is changing to a new steady state, like when the Sahara shifts back and forth between forest and desert, human activities can speed that along. For an example, the Sahara periodically does make that shift every 40,000 years. And the soil releases moisture into the atmosphere through evaporation, speeding the drying process when humans are farming the area. Currently, we see forests cleared or burned for raising cattle or soybeans in the Amazon in particular. This reduces the size of the rainforest and threatens the critical mass needed to maintain a humid ecosystem. This is also seen in a region we all studied in grade school. Poorly managed agriculture takes nutrients out of the soil, and what was once the Fertile Crescent is now relatively barren due to human activity of farming and water management. I view it as a secondary effect, but one that accelerates some transitions.
Well, that's interesting. Can you explain in more detail then how the water recycling process of rainforests acts as a feedback loop that has an influence on global climate patterns?
Sure, the hydrologic or global water cycle is a series of interconnected ecosystems with changes in one impacting all the others in some way. The sun provides energy for evaporation, and gravity pulls the water back to land and water through rain and snow. A feedback loop is created where the original ecosystem, say a rainforest, is also impacted by all the other ecosystems. I need to give a definition. I had to look it up, so I want others to share what I learned. Evapotranspiration combines evaporation, where liquid water is warmed and becomes vapor in the atmosphere, and transpiration, where water is absorbed by roots and released from the leaves as vapor. And as a side effect, it cools the rainforest. The Amazon is said to breathe moisture, and evapotranspiration puts moisture into the atmosphere as part of that cycle. This forms clouds and generates rainfall, with much of it falling back into the rainforest. The remaining moisture is carried by atmospheric currents to other regions. The Amazon is known to impact rainfall in the U.S. Midwest region, for example. This is a positive feedback loop, sustaining the rainforest by having the rainfall fall very near the area where it came from. For the downside effects, deforestation lessens evapotranspiration, so less rainfall in the rainforest and areas the moisture is taken. The rainforest becomes more susceptible to drought and fire, leading to a feedback loop and possibly creating a savanna where the rainforest was before. The region relies on water from the rainforest for humans to live, so populations would need to either adapt or leave. If these tipping points, the ones with positive feedback loops, come to pass and temperatures accelerate their warming, it would impact our daily lives through food insecurity, poor health outcomes, biodiversity loss, greater levels and likelihood of extreme weather, and rapidly rising sea levels. We're missing what may be our last opportunity to at least extend a catastrophe currently. Dave, why do you think that we tend to miss the importance of feedback loops?
Well, Max, I think it has to do with the training, at least among actuaries. It has to do with the training we've received on how we think about problems and how we model things. And I think that's all led us to a more linear way. A leads to B leads to C, is what I'm thinking of as linear. It's almost like we need to kill the insect and freeze it on a slide to examine it because feedback loops are dynamic and many feedback loops are also reflexive. They create complex adaptive systems. They're significantly more complex to model than the linear ideas that we like. I'll give you an example. A classic feedback loop problem is something we all deal with, which is the situation where we get feedback, but there's a time lag. So our reactions to the feedback are always reacting to what was rather than what is. So if we do that in a competitive situation where everybody else is, getting the same kind of lagged feedback, that feedback loop can easily lead to a pricing spiral, for instance, and that's something that happens a lot. Certainly, it's a well-known phenomenon in property and casualty pricing of the underwriting cycles. A large cause of that is this delayed feedback. But feedback loop analysis, as you just pointed out, is really good. It can actually explain lots of situations where our linear analysis seems to indicate that the behavior going on is irrational, and it just has to do with just not understanding these moving parts. All right, so Max, can you give us an example of an emerging risk scenario that I might want to evaluate after hearing this?
Well, here's an obvious one. On the liability side of the balance sheet, homeowners insurance would be one to look at. How will weather patterns be impacted by even a partial loss of the Amazon? Some areas will become wetter, with potential greater threat of convective storms with hail and tornadic activity, and other areas will face drought and or heat. A lot of that can be done without building out fancy models, just kind of saying, if we had more hail in this area, how would that impact us, and how should we try to hedge that risk in advance?
The next question, Max, are rainforests more efficient than removing CO2 than savannas? You mentioned rainforests changing into savannas. Or why not are they more efficient?
Yeah, rainforests sequester more carbon than a savanna for the same area, with the rainforest holding the carbon in trees and savannas in the soil. But the big issue is really how quickly a rainforest can release all the carbon that's been held in a fire. Soil sequestration is more stable. As a rainforest is deforested and burns, it releases a large amount of carbon and pollution very quickly.
For the Amazon rainforest, a 15-year tipping point would seem like a very short period of time. Something happened in 15 years there. Major change would seem rapid. Are there other tipping points that could happen along with that change in the Amazon, creating a worst case scenario?
Yeah, and some of this gets into some topics that we've discussed on prior podcasts. Historically, once global warming periods have made it to 3 degrees Celsius above the previous stable temperature, then very quickly the temperatures increase another 3 degrees. So a cumulative total of 6 degrees Celsius of increase. It's thought that this is because of several tipping points that provide positive feedback loops. Permafrost is one, we've talked about in the past, with Arctic tundra melting to release the methane that's frozen below. adding a greenhouse gas to the atmosphere. When you see someone poke a hole in the ice and light it with a lighter in Alaska, this flame is really methane that's coming from that permafrost. We've been discussing tropical rainforests today. While the Amazon is the largest, is not the only one at risk. We certainly have other rainforests that are being cleared for palm oil, for example. Rainforests appear on every continent except Antarctica, and Antarctica, as it melts, will likely have a permafrost issue as well, but it's going to be after all the others because it's covered by ice initially. A third feedback loop can be caused by something called the albedo effect. Warming temperatures cause ice to melt, so you replace a white surface that reflects the sun's energy back into space with darker surfaces on land and water that absorbs the energy. The melting ice is directly slowing ocean currents, and ocean acidification could also be nearing a tipping point. Interactions between oceans and other ecosystems have not really been studied much and remain a big concern for me. I think that's where we could see a big surprise that we haven't thought about ahead of time. If these tipping points, the ones with positive feedback loops, come to pass and temperatures accelerate their warming, it would impact our daily lives through food insecurity, poor health outcomes, biodiversity loss, greater levels and likelihood of extreme weather, and rapidly rising sea levels. We're missing what may be our last opportunity to at least extend a catastrophe currently.
Thanks, Max. I usually try to sum up with 5 takeaways, but today I think I'm going to need more. Number 1, rainforests are climate engines. Beyond biodiversity, tropical rainforests like the Amazon regulate both carbon and water cycles through evapotranspiration, influencing weather far beyond their boundaries. Deforestation and tipping points. Large-scale clearing for agriculture, ranching, and mining is pushing the Amazon towards an irreversible shift to savanna, with scientists estimating tipping point within about 15 years. Number 3, feedback loops will amplify change. Positive feedback mechanisms, such as reducing rainfall from deforestation, lead to more fires and further forest loss. This can accelerate ecosystem collapse and climate instability. Number 4, global interconnections. Amazon rainfall cycles are linked to weather in distant regions, such as the U.S. Midwest, making local forest loss a global risk factor for agriculture, water availability, and economies. Number 5, there are multiple climate tipping points. The Amazon's potential collapse could occur alongside other dangerous shifts, including permafrost methane release, the albedo effect from ice loss, and disruptions to ocean currents, creating compounded risks. Number 6, counterintuitive feedback from pollution cleanup. Reducing certain pollutants, like sulfates, can remove a cooling effect they provided, unintentionally contributing to short-term warming. And finally, number 7, implications for risk planning. Environmental regime changes will require new approaches in scenario analysis, expanding beyond linear models to account for dynamic interacting risks with uncertain time lags. So thanks for listening today. Please share this podcast with your friends and coworkers. And if you haven't already subscribed, we urge you to do so that you will get notice of future Crossing Thin Ice podcasts. Thanks. Bye.